talk a little bit about the dynamic node and network addressing. As I've already pointed out in my first talk, that many systems get more and more dynamic in a sense that they are modified by the end user. There's no embedded expert around. We need plug and play capability. The end user only accepts very short boot up times. So, as I said, a good example is always this Pedelec. So a lot of use cases you can illustrate there. And here we have, for example, a power supply, battery pack, or whatever that you want to add to a running system or a simple service tool or something like that. And all that what we see here or what I've said applies to this use case. And now when it comes to dynamic node and network ID assignment, then to run a CanOpenFD system in a proper way, then all of these devices need to have a unique node ID. So the host controller can use the CanOpen services such as the USDO and can now access all the devices. So we have learned already by my talk or by Torsten's talk that we have the possibility to establish dynamical cross communication. And this means also for new devices, I can access these devices, read out their object dictionary, learn about their origin, their functionality, and can embed them as a host controller dynamically into the system. Or I can even make some assessments whether they are even allowed to be present in the system at all. So, but the interesting point is always, how can I get these unique node IDs to this dynamically attached devices? In particular, if this is the end user who has no idea about CAN at all. So often seen in other systems where this dynamic attachment of devices is needed, is a solution like that you have at all the, let's say, open ends, you have a kind of router device, bridge, and you say, okay, when you have your new device or your device you want to add, it typically comes with a default node ID. Let's assume it's a default node ID 1. Then you can plug them directly at this interface, and via the bridge, then all the CAN services are somehow remapped. And then to the rest of the system, you already talk with the intended node ID, for example, the 65, 127, and 66, as they should have, as we saw on the previous slide. So this is a solution for this use case. So the end user has no need to have any CAN knowledge. He just plugs in the device and it works. And the knowledge of the transfer of the frames and so on is then embedded in these nice devices that you have to install at all the interfaces where plug and play in this way is needed in the field via these, I call them transparent CAN router devices. But it depends on the application, whether you want to have this, whether there's even space for these kind of devices. Or whether you say, I don't want to have them, I have no space, I have no possibility, and I want also to save money and maybe also hardware. And therefore, why not shifting this intelligence of the node ID assignment to a host controller, which is anyway available in my application? So exactly something like that, do the layer setting services, dynamic node ID assignment, and for CanOpenFD, we have extended this also to network ID assignment. It works one-to-one as the node ID assignment. So therefore, in all the slides, mainly I talk about node ID assignment, but you can apply all that, what I say, also to the network ID assignment. Yeah, so this means as long as there's devices you want to attach to your system are working with LSS, then they come with an invalid node ID, or let's say they don't have a node ID and indicate this by a specific value. So they are no longer delivered with a valid node ID, but with an invalid one. And a host controller has then the capability via the layer setting services to monitor his network, to see, okay, there are new devices attached. Then it can select and identify the new devices and assign node IDs. And therefore, we don't need anymore these transparent routers or bridges. So you treat one after the other and give the devices the intended node ID value. Yeah, so, and at the end, you have your node IDs dynamically handled. And of course, this we have to do in a rapid and a fast way. As we've said, the end user wouldn't accept too long downtimes, but he or she wants to see rather immediately that the devices are working. So this places also some pressure on these scanning algorithms that you need and the services for finding devices and making them work. Yeah, and not just for CanOpenFD, but already for CanOpen Classic, there were the layer setting services invented, and they were, as I've said, invented to identify not configured LSS server devices. So let's say CanOpen devices that are dynamically attached to a system, they have no node ID, and then they should be somehow be treated by a host controller. Let's call this host controller now LSS manager. And this LSS manager should have the possibility to distinguish between all unconfigured devices, LSS servers in the system. So it's not a rule that there's just one, there may be several attached in the very same time. And you have now the possibility via these layer setting services to identify these devices, to distinguish between these devices, to select one and configure then node IDs. And then with regard to CanOpenFD, also network IDs. Additionally, but not topic of the talk, these layer setting services allow to switch during runtime from one bitrate to another. This is a great feature under laboratory conditions. So for firmware update and others in the field, I wouldn't recommend this necessarily, because there's a certain probability that maybe some devices do not really get the right switching command, and then you have at the end of the day a system that is not working because some parts of the system are working on different bitrate than the rest. So, but nevertheless, this is at the moment not the point. So let's focus on the node ID assignment and network ID assignment. And we see here the initial approach of the layer setting services, CiA 305, provides us with a state machine, so a device that awaits to be treated by LSS manager and shall get that from this LSS manager the node ID. Such a device maintains a state machine, so it is usually in a LSS waiting state where it waits, as the title says, for further commands, and then in a configuration state where typically switch exactly one device in this configuration state in the system, and then I can treat this device, hand over a new node ID, store that node ID setting, and so on. Yeah, so it's a normal CanOpen device, and this CanOpen device, in addition to its normal 301 services, supports now also the LSS server functionality. Don't be confused, I'm already transiting to this new term, server manager. So as some services still carry the old term, so I added this also here. Yeah, so the layer setting services provide me with a mean to hand over a new node ID, and the server can say, yes, I accepted it, or for whatever error reasons, it's not possible, please propose another one. So rather simple protocol with two telegrams. They are coded in a CAN classic data frame format. And I have another very simple command to switch the devices in these state machines. So we see here, I can switch between LSS waiting, LSS configuration. So in a global way, one telegram, all devices go to configuration, all devices go to the waiting state. That's easy, and this remains easy if there's just one LSS server in the system to be treated. If there are more, then we said, okay, we need somehow to differentiate between the devices and to select a single one. And therefore, we have another service in LSS. It's the so-called switch state selective protocol. So the fathers of the 305 specification of the LSS services, they said, there exists something nice, this vendor ID assigned by Canon Automation, and therefore Canon Automation allows to distinguish globally between all the CanOpen device manufacturers by means of this unique value, the vendor ID. And all the manufacturers, based on the vendor ID, have now the possibility to distinguish between their devices via the product code. The revisions of one product can be distinguished via the revision number. And finally, one candidate of one revision can be selected by the serial number. So in total, the vendor ID, product code, revision number, serial number, this 128-bit composed of these 4 times 32-bit addresses is one unique address for one CanOpen device in the embedded world. If you maintain these values correctly, then there can't be a second device in the world that claims the same address. And as this is the fact, then the fathers of the LSS specification said, okay, why not calling the device via this address? Therefore, the synonym for this entry 1018 in this case is the LSS address. Why not calling a device via its LSS address and saying, okay, this device with that vendor ID, product code, revision number, serial number, this is requested to transit to the configuration state. And therefore, I have now a selector to select a single device out of several without no valid node ID and say, okay, that device shall go to the configuration state. And then afterwards, I hand over to this device a node ID and the device can start up into the big world of CanOpen. Yeah, for a manager, it is important to know these LSS addresses of the intended devices. Therefore, he can maintain a database in its local object dictionary, which devices should be available in his system. And of course, if he detects some new ones, then he can dynamically maintain these lists and can add these newly detected ones. But why should he detect one? Yeah, so not necessarily the manager knows which kind of devices are added. So, for example, in case of a service, then you say that you have a broken device, you remove it, you add a new one from the same manufacturer, will have the same product code, but maybe will be for a new revision or serial number. Then you need to identify this new device that substitutes the old, the broken one. So it will have the same vendor ID, it will have the same product code, but it will differ in revision number and serial number. And then you have to search. And this was this identify remote slave protocol. And then you can double check, is there a device out there that matches to this scanning range? And if yes, all these devices under with the frame classical CAN 7E4 and say, yes, here I am. And so by narrowing the limits of revision number and serial number, the host controller, the LSS manager, can now identify a single device. So we here have some scanning cycles. You see in this broad range, okay, there is one device that is unconfigured. Then you narrow the limits, maybe further for the product code. Then you have double checked, okay, is there a further device with that product code? Finally, you have identified the product code, and then after certain scanning cycles, and then you can go ahead with the serial number. So it will be a rather long-lasting task. And we see furthermore, in this protocol, we cannot scan for vendor ID and product code. So as I said, the idea behind was, okay, it will anyway be the same vendor, it will anyway be the same product code, but the devices in a service case, they differ in revision number and serial number. So I have here limited possibilities to scan for devices, and as soon as I found one, then I can store this information, so I don't have to scan another time for such a kind of device, so I can accelerate. But we know now, okay, companies are purchased, so then also the vendor ID will change. This means we need other means for scanning for unconfigured devices. And therefore, the next step was the layer setting services fast scan. And here, the LSS LSS gets the functionality to scan according to certain bit patterns. So I have an ID number, which is a share of the LSS address, either vendor ID, product code, revision number, or serial number. And I can say, okay, according to a certain amount of bits, I say LSS server has to equal this proposed value. And then I identify a certain bit position and say, okay, at this bit position now, the LSS server has to be equal as well. And all the devices that LSS servers that are unconfigured and taking part in the scanning cycle, they will now double check, okay, do we have this part of the ID number? And if yes, they say yes, we have that. And so the LSS manager knows, okay, there's at least one device unconfigured with this ID number and can then go on and can go on until he has identified the entire ID number bit by bit. And this means via the LSS fast scan, we have now a significant improvement because the host controller can scan for, a vendor ID and a product code. This wasn't possible in the past. You can identify a single ID number within 32 requests. And we have now the possibility, based on these functionalities, to support more comprehensive scanning algorithms at the end of the day to accelerate. And now, when it came to CAN-FD, we say, wow, great. We have now the 64 byte of data. Now, there must be some possibilities for improvements for the LSS as well to accelerate. And then we were double checking and we're saying, so yes, in theory, this would be great, but we need from time to time also that several devices communicate the same frame at the same time. In classic CAN, no problem, if you consider some boundary conditions. But in CAN-FD, this is no longer possible. So in CAN-FD, not only because of the bitrate switching, but also of other things, it is not possible that at the same time several CAN-FD nodes send the very same frame simultaneously. This will lead to errors. So therefore, we still need at a certain point the classic CAN for LSS. So I just remind you a little bit on the bus access based on arbitration in CAN-based systems. So if two CAN frames are competing for bus access, then they are getting access according to their priority coded in the CAN identifier. So a CAN identifier, there resides on the one hand a unique number for this frame as well as the priority. So you have this arbitration mechanism, it goes directly via the bus. So this frame with the lowest number, the highest priority gets access, the other one is postponed. And for furthermore, there exists the rule, okay, CAN IDs should be assigned uniquely in CAN. This is true also for CAN-FD, as I've said, very strongly. But as I've depicted here now, for LSS, we say, okay, we make a request, we search devices that follow a certain attribute. For example, don't you have a certain valid node ID? And then the devices should answer in parallel. So simultaneously, they should answer, okay, yes, I support this feature, I support this attribute, I don't have a valid node ID. And for allowing that, you need CAN Classic. The data content needs to be 100% identical. And as you have no possibility to differentiate via the CAN identifier, and you need a classic CAN data frame. So, and you see here a little bit the progress we made. We have now a new version of CAN OpenFD layer setting services based on CAN-FD, and let's see what we have done. We have extended the LSS state machine. We have now a passive state in addition to waiting and configuration. We have learned there may be two reasons. The one is that we have devices that, for whatever reasons, always disturb our scanning cycles. Another may be that by intent, I want to have redundant functionality in my network. Then I can place these devices into the passive state. They will be there, not powering up. And if I need them, I can fetch them from the passive state and then they come up and offer their functionality. And furthermore, we adopted a little bit the services. We introduced something that is the switch state selective FD service, which merges the functions of the switch state selective service and the identify remote service. So I can identify a single device and switch it to the configuration state by the same service. So we could simplify the services, and where it is possible, there we tried to also benefit from the KNFD frame size. An example is if I have one device at the configuration state, switch there via the global command, and then we say, hey, just give me your LSS address. Then we see here, okay, I have just one frame, one request and one answer frame, and I get the entire answer in one frame. Here's my LSS address, vendor ID, product code, revision number, serial number. And as I've already said, fill always up to the next supported frame length. Therefore, we have here 2 padding bytes. And we have here a segmented byte. This is for controlling segmentation. I will say some words later on why we should here consider segmentation if we don't have the need to do so. And furthermore, we used now the FD frame in the switch state selective command for FD, where we said, okay, we have not just an ID number as in the fast scan, but we have the entire LSS address now in one KNFD frame. And we identify via this NIP value, okay, which part of the LSS address shall be equal to the LSS server's LSS address? What are the next 4 bits of this LSS address that we evaluate? And then the LSS servers can give me the response, okay, I'm in the scanning cycle. Here you, in fact, have a device that is that has no valid node ID, and please go ahead in scanning in this direction to get this device. So why are we talking about nibbles here? You see here, we introduced a pattern according to splitting up the entire LSS address in nibbles from nibble number 0 to 31, because we reminded us on the network access methods in CAN, the arbitration. And we said, hey, there are 15 decimal values available. This means the size of a nibble where my devices, there we have, we used the last digit of the CAN identifier with the size of a nibble, 4 bits, where we could say, hey, we can use now this nibble and could give the servers the possibility to inform the manager about the next 4 bits in the response of the CAN identifier. And this is a great evolvement, because this allows us accelerating the scanning, because now we have for the first time the capability at the LSS servers to say, okay, you don't have to scan around for the next 4 bits, but I give you already the value of the next 4 bits. And then the LSS manager can enhance his next inquiry with the next 4 bits where he knows already. Maybe he got 2 or 3 next 4 bits values from the server, so he can also store them for allowing comprehensive scanning cycles, follow in one direction till one LSS server is entirely detected, assign a node ID, and then go to the reminded values, and then he can continue there, and therefore he can dramatically shorten the time for identifying unknown LSS servers in his system. Furthermore, there would be also the option to accelerate this furthermore if you use the extended frame format. So Classic CAN as well as FD offers 2 frame formats, the base frame format with 11-bit identifier and the extended frame format. And if you're using the extended frame format, we reserve for the CAN identifier in the extended field 16 bits, where the LSS servers have the possibility to inform the LSS manager about the next 16 bits of the unknown LSS address. And therefore, you can dramatically shorten the times for scanning. And yeah, this is the biggest improvement that we reminded us, hey, there can be a feedback from the LSS servers to assist the LSS manager in scanning for unknown devices. So the LSS switch state selective FD introduced significant improvement, as host controllers can now identify an entirely unknown LSS address within 32 requests only. So I can identify these services with 8 requests by using the extended feedback, so the 29-bit identifier. And furthermore, adding comprehensive scanning algorithms on that allows a rapid detection of devices in my system, of dynamically attached devices to my system, and therefore I can keep the downtimes of my system or the attached devices very low. Yeah, when we were developing that, then we also reminded us that it is unfortunately the fact that it took a while till KNFD entered up the market and came into was available in several applications. Therefore, we thought it is wise to offer this functionality also to CAN classic-based systems, so to CAN Open Classic systems. And therefore, we provided a document CiA 702 where we mapped this functionality to classic CAN frames. So this document says, how does all this new functionality work without the usage of CAN-FD frames? So therefore, it's also available in a CAN classic environment. So for new design systems based on CAN classic, this can be also a very attractive candidate. Go to 702 and see how you use these services in this environment. And therefore, I said to you, I like you to remember the seg field. So here I use it now for indicating which segment of this now segmented service do I transfer. Yeah, so much with regard to enhanced detection capability of dynamic added devices, so dynamic node ID addressing, dynamic network ID addressing. So as I've said, system designers have to guarantee minimum boot up times for dynamically changing systems. And therefore, we have now the documents here 1305, the CAN OpenFD layer setting services that provide an efficient LSS service transfer by using CAN-FD data frames, where it is advantageous and possible. So we cannot send simultaneously from different devices the same CAN frame in CAN-FD. The feedback allows us to identify unknown LSS servers in a very reduced time. And we have furthermore the document 702. If you're still staying with CAN Open Classic systems, then you see how you can use this added functionality also in these kind of environments.